Okay, I think we got through freezing point depression. Here's the freezing point depression. Yeah, I've got some markings on here. We got into boiling point elevation, similar equation. We didn't get into the derivation of it all, and neither did our author. He just referred to the fact that deriving it similarly, we get a boiling point elevation, and another unusual name for it, ubuloscopic constant, is another name for the boiling point elevation constant. And we even started talking about osmotic pressure. Yeah, and Grant, I think again you had some.
I was lost.
You were lost.
We talked about it in Chem 2. We only talked about it once, so I was very thankful.
Okay. Well, let me just back up for a second
To some extent.
for the engineer in the class and explain why it is so important. Let's pretend this is the cell.
Well, you have the potassium and stuff going in and out.
Yeah, well, let me do a better drawing. Let's pretend this is a cell, and Grant, have you heard the term lipid bilayer?
Yes, learned about that in 10th grade.
Okay, lipid bilayer.
There's phospholipids and then lipids and then
All right, and now with your great appreciation for polar molecules, nonpolar molecules, we have a region here that is nonpolar. It's lipids, fat. And what do we have out here? We have an aqueous solution. And what do we have inside the cell? Aqueous, polar. And what do we have floating around out here is a lot of things that are soluble in polar solvents. And so so you have to get across that semi-permeable membrane with it, which is a lipid bilayer, to get in and out of the cell by either active transport or diffusion or whatever. Water can get through here pretty reasonably, or there's ways for the water to get in and out of there pretty easily, and everything else is a problem. So what you want is a let me look at the terms. There's hypertonic, hypotonic, and isotonic. You want an isotonic situation where the the concentration inside the cell and outside the cell of ions is equal. If you get that unequal, then osmotic pressure will drive the water in or out of the cell to equalize, to get it back to being isotonic. So if it gets to be hypertonic outside the cell, water is going to go out of the cell into this area around the cell, and it's going to shrivel the cell up like a raisin. How did this happen? In the early 1900s, they started thinking when someone's dehydrated, we need to, when they were first starting to think about intravenous things, they gave pure water. And it stressed or even killed the patient by injecting pure water into the veins. What they did by that is, that would dilute out here. This would become dilute. And the water would, which way is the water going to go? So now we got a hypotonic. So water's going to go in to raise the concentration on the outside, and what happens? The cell bursts and dies. So you have a sick person already, and you're stressing them by intravenously giving pure water. And what is driving that? It is ice. It is osmotic pressure. There's an osmotic pressure. So if we get back to the laboratory situation, we don't have a cell, but here we have our semi-permeable membrane, and here we have, well, let's start out lower. We have stuff over here, and we have just water over here. Water and whatever's in there. Could be sugar, could be salt water. It just has something dissolved in it. And so to try to equalize the concentrations on either side of this membrane, water goes in this direction. So this goes down and this level goes up.
But how's gravity not going to get the water to go back over?
Well,
Gravity caused an increase. So there's just an increase in pressure on the left-hand side. So more pressure at the bottom.
so what you have right here is atmospheric pressure, and what you have right on this here is atmospheric pressure, but you have in addition this osmotic pressure.
Yeah.
So the atmosphere will not push that back in there. The osmotic pressure is a pressure that's drawing water into here.
I didn't mean the atmospheric pressure to be pushing it back in, but there's that extra height of water, and so that extra height of water causes an increase in pressure at the bottom. So if you have like that semi-permeable membrane, like how could water just not get pushed out? So you know what I mean?
Well, I kind of know what you mean, but here is a kind of another driving force. This is another driving force over and above gravity that is driving the water over here against gravity. Against gravity, it's rising that column of fluid upward.
Interesting.
And it settles there. Now, if we had another one over here, let's say we had another one, and the concentration here is 1 molar. The concentration here is 2 molar. We should probably be talking about molality. Molal, 2 molal. What you're going to find is that is going to be, it's going to be a bigger separation in the heights of those two columns based on the concentration.
These are just going to be 2 times higher. 2 times increase in concentration.
Let's look at the equation here. I think it would be just a factor of 2 different. Now the concentrations never get equal, okay? You still just have pure water over here. And you still have a solution over here, but it's much more dilute. A much more dilute solution here. So it never accomplishes equal isotonic situation, but it is going in that direction, and it reaches a point of equilibrium where now it's pressing against atmospheric pressure. It can't do anymore. Okay, now to take it out of the biological thing and get it into my kitchen, and maybe some of your kitchens, an RO unit, reverse osmosis, is starting with your drinking water, with your tap water here that has some stuff in it, and it applies a pressure on here. It presses on here with a pressure greater than atmospheric pressure, and it's driving this level down, and the only thing that can go over here is water. And then this becomes your drinking water.
Are these just like filters in your fridge, or?
No. These are units underneath your. Well, I just got one installed. I just moved up here. We just had one installed. It's underneath the kitchen sink. It has 3 cartridges, a carbon cartridge, a semi-permeable membrane, the RO cartridge, and then a finishing cartridge of carbon, and then a reservoir tank under there, which holds about 10 liters of drinking water, and it just fills that tank, trickles that tank in there. And it's using your tap water pressure as this pressure here.
So, but it doesn't take out ions.
No, it leaves them over here at a higher concentration.
Well, so in the lab we have an RO machine, and then we have a milli-Q, which is to purify it further to get deionized water. Or like, so it does, like, what does this actually take out? Does it take out like everything, or just?
It reduces this load here by 95%.
Okay.
So so lead, any of that would be knocked down 95%. Sodium, potassium, chlorine, all that stuff. So a reverse osmosis. So normal osmosis is the water is driving into the thing. So so Grant, you're struggling with the intuitive. Doesn't intuitively sound right. Gravity should.
Yeah.
But no, this is actually a force. This is a force that's driving the water in to the solution to lower the concentration of the solution. And here's the equation. This capital pi is the symbol used for osmotic pressure. And here's kind of some of the background. The change in chemical potential. At constant temperature, we just have volume times the change in pressure. We get in, and we can get down to this equation: pi times the molar volume equals the mole fraction of the solute times RT. Now, those of you reading the book, you kind of recall there was an earlier Van 't Hoff equation. So there are actually two equations called the Van 't Hoff equation. They're not really related to one another, but here's another one. So Van 't Hoff got into osmotic pressure.
What is OX? Yeah. It's a mole fraction. So like, yeah.
Now, as I was looking at the homework this morning, I was surprised to find that I had not chosen an osmotic pressure problem for your homework. There doesn't seem to be one in there. I think there's only one or two at the back of the book. But as I was putting the homework assignment together, it escaped me that we weren't addressing this in particular. Okay, let's just apply it real quickly. What is the osmotic pressure of a 0.010 mole solution of sucrose in water? What pressure would that generate? We know this. We know this. We're assuming just right at normal temperature, so we know the temperature. We want to calculate this, and the okay, we hear this is molality here. And so to convert that into a mole fraction, This number here is almost negligible. Here is the number of moles. So this is going to be grams per kilogram of water, grams of the solute per kilogram of solvent, kilogram of solvent, 1,000 grams of water, and there's its molecular weight. It really should be 18.02, don't you think?
Probably.
At any rate, so 55.5 plus a little bit here. This would be the mole fraction of the solute. So molar volume of the solution, we're just assuming it at such a low mole fraction of solute in here, we're just taking pure water. What is the molar volume of the solution? 0.01801 liters.
If there was a higher concentration of the solute, how would you find the molar volume?
Well, you'd have to be given a density of that solution.
Okay.
Something like that, like if it was 6 molar sulfuric acid or something like that, you'd kind of need to know the density. Usually, yeah, that's what you'd have to work with. So here's the pressure. That's a pretty dilute solution of sugar, and it's generating almost a quarter of an atmosphere of pressure. That's a lot of pressure for a very dilute solution. The book goes on to kind of compare this to, it has a little baby giraffe standing there that might be, it has you go on to calculate how high would that drive a column of liquid, that pressure. And so osmotic pressure can kind of be involved in even this little giraffe that's got its heart beating and trying to get liquid up to its brain. It can also be an osmotic pressure that might assist with that.
So we could use atmospheres there too. We could use 8.08205 and get atmospheres as well. So for the R value,
Yeah.
Right.
they're just using bars.
Yep. Okay. And let me see here. Take a look at the end of chapter 7, and under the problems there, you get into colligative properties. And there's, let's see, which problem? Oh, I don't have this, but here's the picture. Here's the picture I was trying to describe. This is a pretty classic picture. This is the blood cell. This is like a red blood cell, normal, isotonic. So the concentration of electrolytes around the cell and the concentration inside the cell are isotonic, are equal. So here, I think here's the situation where it's hypotonic, where you would have perhaps put pure water into someone's bloodstream. I mean, we can drink the water, but our digestive system sorts that out. It's going across a semi-permeable membrane in our digestive system. But to just to take it intravenously into the bloodstream, pure water, it's diluting out the interstitial fluids, and it's going to cause the red blood cell to swell and possibly burst. So it's going to stress or actually kill the red blood cells. And here's the case where the red blood cells is having the water sucked out of it because of the high concentration. This is the reason why you can't drink seawater when you're out in a boat and you're thirsty and you're tempted to drink the seawater. It's going to dehydrate your cells. the high concentration of salt. Yeah, and yeah, so they're very, very critical, very key biological, physiological aspects to osmotic pressure. And it is a real pressure. Okay, I was on my way to looking at the back here. Well, the one other example that I didn't show here was example 716. I don't think I have another slide, do I? Oh, okay, I'll mention it here. An aqueous polyvinyl alcohol solution that is made by dissolving 0.01 grams of polymer in 1 liter of water has an osmotic pressure of 0.0030 bars. What is the average molecular weight of the polymer? Assume 298 K. We won't go through that problem, but I just want to point it out to you. You could look at that. This is one way of trying to estimate the molecular weight of a polymer by looking at its what osmotic pressure it would develop. You can weigh a polymer, let's say you made, make up a solution of it, see what osmotic pressure it generates, and then back calculate the molecular weight of the polymer. The author also points out, getting back to colligative properties in general, that when in organic chemistry, when you synthesize a molecule, what is the main thing you do to look at the purity? What do you check? When you've made synthesized, let's say you're synthesizing benzoic acid, and that you actually went through a synthesis to make benzoic acid, and the question is, how pure? You made it, okay, you got 5 grams of it, how pure is your benzoic acid?
Qualitative or melting?
Qualitative melting point. Check the melting point. Why do you check the melting point? Well, you check it against pure benzoic acid. It has this melting point, and it's always going to be lower than the pure compound. If it's very close, it's pretty pure. If it's been depressed a bit, then based on the freezing point depression.
Equations to actually get percent.
Yeah, I think you could get an idea of the level of impurities that are in there. Yeah. All right, so that's freezing point. You check the freezing point of your organic synthesis and you say, yeah, it's pretty pure. Okay. Well, let's leave chapter 7 there for now, other than the homework. Take out the homework and let me see what questions you're having. I have a candidate for throwing out one. Which one do I want to throw out? How about 7.31?
Sounds good.
Yes.
Yeah, because the question I read through it a little bit more carefully now. It's either a little bit ambiguous or I'm missing something, because it gives you the mole fraction of nitrogen, and then it asks you to calculate the solubility of oxygen. So I didn't even.
There's a lot of air stuff I feel like you'd have to look up to get this question right.
Yeah.
Like what is air and.
It tells you it's 80% nitrogen, 20% oxygen.
Yeah.
But it's giving you the mole fraction of nitrogen in water. I don't.
You could solve for the mole fraction.
In my mind, we can drop that one.
Sounds good.
So cross out 31. Now, it doesn't mean we just cross out every one we struggle with. So which ones are you struggling with? I'll tell you, there are a couple easy ones. Don't make them very hard. 728 is straightforward. 726. I'm not getting the answers the author has. It's straightforward. Seems to me it's a pretty straightforward problem.
726.
Pretty simple.
What does the author have? Is it in the back of the book?
Yeah.
Say it.
What did you get?
1.25% of the 6.
That's what I got,
Yeah.
and that's what I got, and the author has this and
Yeah.
this.
That doesn't make any sense.
Yeah, so I think the author's wrong.
I mean, yeah, it was really easy. It wasn't. It was
Yeah.
look up a conversion factor.
Right,
It was
right.
from Google. It
It's
wasn't.
just doing conversion factors.
For 26, did you even pick another table?
Try to round it as close as possible. Okay. Yeah, I learned that one.
Okay.
That one I got that as well.
Yeah. Oh wait. You got to.
You know, you them all.
Yeah.
So on 726, just make a note to ignore the book.
Yeah, yeah.
It's pretty
I
straightforward
could be
and
wrong.
simple.
I could read
I don't know. I'll retake.
I'll just ignore the book
Okay.
answers.
Because I think he got. The author said it was to the third, but we were not sure.
46 days left.
728 is straightforward. 730 is reasonable. 731 we can drop. And I haven't done all these problems, so
Can you drop one of the math book ones? You'll usually take a lot of time to do it.
The third, yeah.
Okay.
The bottom one.
I feel like those are normally more like your type questions. Like
Here.
you drop stuff that are rather drop it.
This one, I think, I actually ended up getting to the third because this is 8.
yeah, that's what I have.
Oh,
I have it
yeah,
to
okay.
the third.
Oh, never mind.
I
Never
have
mind.
it to
Then
the third.
Then we, yeah.
I didn't write it very well.
Oh, well.
Yeah. Okay.
Rounding error.
Yeah, Liz, yeah, there's only about 4 that are not in the book, right? 4 of them not on the book, 5 maybe. Only, I say. All right, I didn't plow through all of them yet, so I'm going to just drop 731, and I'll try to work down through some of these other problems. You can ask me some more on Wednesday. Any other questions about chapter 7?
Did you use 7.35?
Not yet, I haven't.
Because the author got 2.78 molar and I got 2.61. I don't know why. It seems like a pretty straightforward, like, get a mole amount, change it to grams.
What you get
I got 2.61.
in the book?
The book says 2.78.
All right, I'll do it and before Wednesday. See where it's coming out.
We don't know what that means.